I don't want to play against you.
All right. Good afternoon, everyone. So,
Starting, guys.
yeah, we are starting. So, thanks for joining the session. Today's tech topic is unlocking data, the power of Postgres text search. So, Postgres is very popular open source relational database. Apart from offering robust transactional capabilities and relational model, it also offers very powerful text search capabilities. In today's presentation, I'm going to cover three different type of text search based on the characteristic. The first one is basic text search, including pattern matching. This is most commonly used text search type. If you have worked with Postgres or any other relational database, this is what you have used. It's just a normal search used in day-to-day work. Example includes finding all the students with given last name or finding all the student whose last name starts with given prefix. Next is full text search. This includes natural language processing like tokenization, normalization, ranking, etc. Pre-processed result is stored and later used while performing text search. Example includes finding all variation of the word in an article. For example, fly, flies, flying, all gets matched while searching for the word fly. Both basic text search and full text search are supported out of the box. That means no additional configuration and or installation is required in order to use them. The next one, which is similarity or fuzzy search, is offered as an extension. Once it is enabled, it allows detecting misspelled word. So let's start exploring more about basic text search. As discussed, this is most commonly used type text search, whether there is a need to find out all the orders in a given status or whether there is a need to find out most frequently occurring error code. Basic text search type is more than sufficient for most common use cases. It also has full support for regex for pattern matching. However, there are limitations. For example, it does not support ranking. When there are thousands of matches are found, there is no way to display most relevant result on top. It also can't work with the derived word. For example, satisfy satisfies. One is singular form and the other is plural form. Basic text search type can't detect derived words. Basic text search type on its own is not sufficient while working with large data set. So there is a need to have index type that makes it possible to perform the text search efficiently and quickly while working with large amount of data. Please take a note that index is not mandatory in order to perform the text search. However, it is often desirable while working with large amount of data. B-tree is the go-to index for basic text search type. It is also the default index in Postgres and many other relational databases. That means when you create an index without specifying index type, Postgres creates the B-tree index. Only B-tree supports unique indexes. That is the indexes for primary keys and unique keys. B-tree is useful in performing search, sort, and join operation. Faster data retrieval is made possible by reducing the I/O significantly. It is able to work with large amount of data set because it is based on the disk and not restricted by RAM. It offers order of log and time complexity for search, insert, and delete operation. So just would like to check if anyone knows like what exactly order of log and time complexity for these operations. If
Yeah, me and Jacob just took an exam on this.
So what exactly is order of log and time complexity?
It means that the way I see it is it's like it's logarithmic in searching so that it's faster and faster, not faster, faster.
Faster than linear, right? Slower than constant.
Yeah, it's faster than constant time. I think of it as it's the inverse of grammar. So it's easier and easier to search for as you go through the data.
Yeah, that's the more way to describe it. So the time it takes to search grows slowly with respect to the data that can grow substantially, basically. So how does B-tree achieve such a high performance? So in order to understand that, we need to take a look at the structure of the B-tree. So B-tree is a balanced tree. That means all the leaf nodes are at the same height from the root node. B-tree continuously performs rebalancing in order to ensure that all the leaf node remains at the same height so that consistent performance can be delivered. All the keys within the nodes are stored in a sorted order. It's a multi-level tree structure where each layer can be considered as a doubly linked list of pages. So there is a fixed meta page which has a pointer to the root node. Root node has a pointer to internal node, and internal node has pointers to the leaf nodes. Leaf nodes has a pointer to all the table rows with key one key. Now there is often a discussion about Postgres implementation, whether it's a B tree or B plus tree. So what's the difference? Like, does anyone knows about like difference between B tree and B plus tree? Like anyone online?
You have to remind us.
Okay. So in case of B tree, both leaf nodes and the internal nodes can contain a pointer to the actual table rows, while in case of B plus tree, only the leaf nodes can contain the pointer to the actual table rows. And Postgres implementation is closer to B plus tree. Now let's perform the search operation, basically the simplified version where how we will locate a key with value 12. So the search will start with the root node. 12 is getting compared with value 6. Since 12 is greater than 6, we'll follow the right pointer down the tree and go to the next node where we found that 12 is less than 15. So we'll follow the left pointer and we'll go to the leaf node where ultimately the key is matched. Of course, the actual search is much more involved. So how does it might look like? So Postgres stores the meta page about the index and it has a block number for the root node. When I say root node, it's actually a page or a block that can contain multiple keys. Within the page, all the keys are stored in a sorted order. So Postgres will use this block number and load the root page from the disk into the main memory by performing the IO operation if that root page is not already in the memory. Once the root page is loaded into the memory, binary search is performed. Since all the keys are sorted, now, at the end of the binary search, since the root node has only one key, it will point to this particular key. Basically, the goal of the binary search is to find the minimum key, which is greater than or equal to the search key. In this case, there is only one key, so it will point to the only key. And then comparison is performed. Since 12 is greater than 6, we'll follow the left pointer. When I say left pointer, it is a block number for the next page down the tree. So Postgres will perform another IO operation and load that page into memory. Again, the binary search is performed. And since 15 is greater than or equal to 12, binary search will point to this key with value 15. Now the comparison is made. Since 12 is less than 15, left pointer is followed, which is nothing but a block number to the leaf node. So Postgres will perform another IO operation and load the leaf node into main memory. And again, the binary search is performed and the key with the value 12 is loaded. Once located. Once the key is located, it will have pointers to the actual table rows. Now the Postgres needs to retrieve all the page containing those rows. Please remember that Postgres doesn't retrieve one row at a time. For efficiency, it always loads the entire page. So all those rows containing the value 12 will be loaded by performing IO operations sequentially. And to put into perspective, just by using 3 to 4 levels, Postgres can support millions of rows. Out of millions of rows, we can locate any key just by traversing the tree with fewer IO operation. Okay, I will pause here if anybody has question or comment here.
What portion is this stored in memory versus stored on disk?
So if the
Only
search is
uses
performed,
memory once it's found a page.
okay, so the question that asked is like what exactly is stored in main memory and what is stored in disk. So somebody was speaking like, is somebody answering that question or has another question? Okay, so basically like if the index is used frequently, basically some of the pages can be cached in main memory. In that case, there is no need to perform IO operation. So I was referring to the fact that yes, like basically if it's not there in the cache, basically Postgres needs to perform IO to load that particular page. But if it's already used, the fact that this index is frequently used or this particular page is like frequently part of the search result, Postgres might be able to find in main memory. And once it is loaded into main memory, basically all the keys are sorted. So binary search is performed to locate the specific key within that page. Okay, now let's also take a look at another example for a range query. Let's say if you want to find out all the key with value greater than or equal to 4 and less than or equal to 16. So we'll use the simplified version here. So in the case of range query, basically we need to descend to the tree and find the lower bound. So in this case, the lower bound is 4. So we'll start with root node. So 4 is less than 6. So we'll follow the left pointer, go down one level the tree, and we'll go to the next node. In this case, 4 is still less than 5. So we'll follow left pointer and go to the leaf node, where initial entries will be discarded, but we found that 4 is the lower bound, and we are able to find that in the leaf node. Once the lower bound is located, all we have to do is just follow the point link, basically. So it's a doubly linked list of pages, basically. So we'll go to the next page, and again, the search is performed until like upper bound is found. So we'll reach till the node which has a value 16. It also go to the next node where it will found that like 18 is like greater than the upper bound, basically. So it will stop there. So this is how the range query is answered efficiently. Any questions, comments? Yeah.
How expensive is it if you insert new values? And you index those values? Can you talk about that?
Okay, so like I can go up to certain point. I didn't explore because this is mainly focused on text search. Yeah, exactly. So basically, it's a shallow structure, and it needs to ensure the property that all the leaf node remains at the same height. So it could be expensive. So first of all, like basically it needs to anyway perform the search in order to locate where that key needs to be inserted, which is like follow the same search path that we just now followed. Once it reaches there, now in case of insert, basically like new page might needs to be inserted, and new page might needs to be created. Now in case of delete, basically like maybe at the end, like there is nothing left in the parent, and like it might result in restructuring the large portion of the tree. Yeah, it's possible that index and delete operation can get expensive, but the version implemented by Postgres is optimized for concurrency. So initial B-tree index, like created at the Boeing Research Lab by Bayer and McWright, which was revised by Lehman and Yao, and Postgres again optimized it. So Lehman in Yao's algorithm optimized the initial B tree for the purpose of like concurrency without like no locking at all. But the Postgres implementation requires locking. It's minimum, like just couple of, but with minimum number of lock, basically it can perform insert or update operation. So it's definitely like, the as we have looked in previous operation, it's insert and update operation are also of the logarithm of n. So Postgres takes care of all this complexity behind the scene, but still efficiently. All right, yeah.
Another quick question. For finding a range of values in the nodes, this example, would that be a linear time complexity since you have to go through each link? Or can it be logarithmic since it's sorted on the upper bound and kind of grab that range?
Yeah, so the question asked is the example that we last went through where we did the range query search, whether it's logarithmic or like it's more expensive. So it's still logarithmic because again, like it depends, like basically the actual answer, it depends like based on the range. If we are looking at a range which spans most of the tree, Postgres might resort or fall back to the actual table scan, but it is like reasonable number. Like there is not a real number, but think about like if it is just 10% of the overall keys, basically it will be still logarithmic because once you descend the tree, you just need to load additional pages. And compared to assume like, we are dealing with large amount of data in millions of rows, you just need to load few pages. It's still like logarithmic. Yeah, but again, it depends based on actual range that you are searching. Any more question? Anyone online? Okay, so let's move on to the next one. So we already looked at like the actual comparison operation and the range queries. So between and is kind of like range query itself. So let's look at pattern matching. With B-tree index, there is certain restriction. Only pattern matching that is supported is prefix matching. If you want to search anywhere in the document, basically like it's not supported. So at one point I said like there is a full support for regex. Now like what exactly is this? So Postgres is still able to support the regex completely. It's just that B-tree index will not be used for suffix search. So to understand that one, let's take a look at the index, which is based out of the actual text. So B-tree also supports the indexing for the text data type. Basically, text can be sorted lexicographically. In fact, B-tree can support many data types, basically, as long as it supports the comparison operation. Even the new data type can be introduced as long as the comparison operator are implemented. So in this case, all the tags are arranged similar to how the numbers were arranged in previous case. And let's take an example for a suffix search. Let's say we want to find out all the name that starts with B. So again, when we start at the root node, B is less than the actual word Kia. So we'll follow the left pointer, which will land to the next level down the tree. We'll perform the binary search and it will point to the bill, and B is still less than bill. So we'll follow the left pointer and go to the actual leaf node. Now here, while performing the prefix search, no match is found. So we'll go to the next node where there is a match found. There is only one key in the next node, but it can have multiple keys in that particular node. We'll go to the third page where we'll find the first entry, and the search will stop when we found that B is less than Eric. So that's exactly how the prefix search is performed, and that's the reason that Postgres has limited support for pattern matching. Now, if you want to search anywhere in the text, B-tree, the structure of index is not efficient for searching that kind of request. And that's the reason there are use cases where we need to look beyond the basic text search. And Postgres has answer for all those kind of queries. Okay, so before we go into that one, let's take a look at the demo for the B-tree index for the basic text search. So in this case, I'm taking an example of the student table where you can see in the down that these are some of the sample data, like there is an ID, first name, and last name. We'll be focusing mainly on the last name. So here we are performing exact match. And if you can see here, the index is getting used, like using the example like we saw in previous slide, that we can easily locate all the students with the last name. For completeness, I'm running all the queries, but like basically like, we have so many matches with those students. This table has 2 million records. Like we needed a large amount of data in order to ensure that like index is actually used. Now, this is another use case. Where we don't even need to go to actual table. This is an example of index-only scan. So this is just want to showcase that in some scenario, queries can be optimized such that there is no need to touch the table. All the data can be served from the index itself. In this case, we are performing the search on the last name, and the result also needed just the last name. So if you see here, there is only index scan, like there is no need to touch table at all. The next is example of range queries. In case of text search, like what could be good use case? So for example, like Caddy wants to take HR session in multiple batches because we have so many employees. So we want to sort batches by the last name of the employees. And that could be one example where we want to perform the range query for a text data type. So in this case, the index scan is performed. Now, if you see here, it says bitmap index. So what exactly is this? Our index is actually B-tree, and why it says bitmap? So sometimes what Postgres does is it retrieves all the pages that has matching rows and loaded into the main memory. And for optimization purpose, like when there are multiple index involved, it can perform bitmap operation to reduce actual IO. So before the actual result is retrieved, we can narrow down the search. Like one example is like one of the index match say 50,000 record, while the other index match just like 5,000 record. So instead of like, retrieving 50,000 rows pages containing all those 50,000 rows, what Postgres can do the optimization is it can take all the table IDs, load them into memory. Same case for the other index, it load them into memory. And if the search condition is AND operation, basically like we'll narrow down all the search result to 5,000 rows. And all we have to do is just retrieve those pages where those 5,000 rows are present. And that's the reason it's a bitmap index scan is mentioned here. Now, let me actually fetch the data here. Currently result is not ordered, but basically like all these names are between M and R. Okay, how about case sensitive search? So let's try to perform all the student which might be in different case. And oops, like, it's a sequential scan on the actual table. So what's going on? B-tree store the data as is into the index. So when we want to perform the case insensitive search, basically like if we look at the ASCII values, basically like the uppercase character comes first and then comes the lowercase, and B-tree has to follow that order. Now, since the data is not optimized for case insensitive search, like it determined that scanning on the table is actually better plan. So how to achieve the case insensitive search? So there are a couple of workaround. One workaround is we can store the actual values in the table in the lower case, and while performing search, we can convert the input value into lower case, and then we can do the case insensitive search. But if requirement is we want to store the value as is, whatever the case was received, in that case, we need to create the functional index. So let me create a functional index here. So it's very quick. Let me run the query again. So now if you see now it started using index. All right, so let's take an example of pattern matching where I say like B-tree index will work for the prefix matching. And if you see, like, it's not using index, like what exactly is going on here. So this is something to do with the configuration, basically, the way Postgres is by default configured. So in order to make the pattern matching work, I need to use text operator. The other option is use collect-C, which uses the byte comparison for actual character actual value. So I'm creating an index using text operator. And now let's run this query again. So now if you see, the prefix matching is now using the actual index, and it converted it into a range query where it used this as a lower bound and the upper bound is like next character to. Any questions so far?
Again, that's like the prefix though.
Yeah,
You can't have any old regular expression in there.
yeah, exactly. So let's so I already created an index and it is used for prefix matching. Now let's try to do the suffix search. And now it resulted in the scanning on the actual table. And that's the reason there are use cases where we need to look beyond the basic text search. I'll just pause here if anyone online has any questions for the basic text search and indexing. Nobody has any question here. Okay. So now I will go to the full text search. This is This is totally different approach to the text search. In case of basic text search, the data is stored as is into the index, versus in case of full text search, the pre-processing stage is involved, which is centered around natural language processing. With full text search, sophisticated text analysis is made possible because it provides very highly relevant result. It allows matching the different variation of the word. For example, fly, flies, flying, all gets matched while searching for the word fly. It also makes it possible to do the phrase search and proximity search. So what is phrase search? Phrase search is when like multiple words are next to one another. And proximity search is one level further than that, where distance among those words can be specified. For example, like if you want to look for the word payment system, so in order for phrase search to be considered a match, payment and system has to be next to each other. In case of proximity search, you can specify that both words can be 3 words apart, 5 words apart, like we can specify the limitation. So that is made possible with the full text search. So what exactly is involved in pre-processing? In pre-processing, the document is passed into a token. Basically, the text is broken down into individual words or a logical unit. Then next, the tokens are normalized into lexeme. So what exactly is a lexeme? It's a normalized or the base form of a given word. For example, run, running, runs, all gets normalized to a lexeme run. All the stop words are removed because they occur too frequently. They will not be useful for text search. Example of stop words are A and D. Then everything gets converted to lowercase to perform the case insensitive search. Now at the end, we'll have a pre-processed document which is optimized to perform the full text search. So what exactly is needed in order to perform the full text search? We need minimum 2 things. One, to pre-process the data. And the second, to represent the user query or the search term. So Postgres supports those building blocks in terms of functions. TS vector is for pre-processing of the data. This is an example where this long text is now transformed into a document which is optimized for search. As you can see, it's all the tokens are normalized to a lexeme and it is stored along with the position in it. For example, the plural forms gets converted into a base form. Also, all the stop words are removed. The special characters are removed.
So is that showing where the location is of each of those?
Yes.
But if the A is removed, why would that be at the second position and not the first position?
So that when after consulting the index, when we want to perform the proximity search, that's when it will be helpful. So proximity search with respect to the original document, basically.
All right, so when you say the stop words are removed, is that similar to saying that when you make this 2TS vector, stop words are just not indexed?
Yes.
Got it.
And also this is stored separately from the actual data. All right, so the next one is, this is another building block. This is basically adds additional capability where the priority can be assigned when there is a structured document. For example, in an online post, there is an article and a content. So basically we can say that word inside the articles are more priority than the word appearing in the content. So Postgres supports 4 priorities, A, B, C, and D. And this is the function using which those sections can be assigned higher priority. This will be helpful in performing search where we want to restrict the lexeme appearing in specific section, or this can also be used for ranking. For example, the word appearing in with particular label is ranked higher than the word appearing elsewhere. Now we need a way to represent user input or that search term. So for that, we have variations of the functions are provided, but their goal is to represent the user query. Similar to the TS vector, it also performs additional transformation. For example, in this case, still the stop word is removed. The first one is the most advanced version of the query, and then it provides high level of support where you don't need to learn more about how to construct the query. So this is another building block for supporting the query. Now we can make a very complex query using this construct. For example, in this case, we are saying look for a word pet or rats in section A and B. Now, if you see here, the plural form gets transformed into a base form here. But basically here we can specify the complex type of search and or not, and then you can specify the distance for proximity search. And many combinations can be specified in order to perform sophisticated text analysis. In the second example, it's a prefix search where we are saying that the first term, as long as it is matching the initial word, will match the result basically. And also at the same time, prefix search, including the label. So it only will look for a specific section where this word is appearing. And this both word has to appear in order to consider the matching result. Postgres also, full text support also has support for the ranking. Basically, there are 2 functions supported, tsrank and tsrankcd. Basically, the algorithm used for ranking is how frequently given word appears in the document. The second variation consider the proximity of those search term appearing in this document. Using this, we can have highly relevant result returned, basically. The limitation for full text search. Most of these limitations are not going to affect a typical use case. So I will cover a couple of them. The one which says that position in TX vector cannot be greater than 16,000. So any lexeme appearing further than that will not be discarded. It will be stored as this maximum value, basically the 16,000. The next one is for each lexeme, only the 256 occurrences are stored. And that is good enough for most text searches. So now let's take a look at the demo. And this demo is only focused on building blocks. So we'll not be performing the actual text search. So this is what we saw in order to transform the user input. So this is same as example in the slide where all the normalization is performed and then lexeme along with position is stored. This is the query example where two keywords are getting searched. This is OR operator. This already we saw in the slide. And these are the variation of the TS query. So in this case, what Postgres does is it removes the stop word, it normalizes the individual word and then automatically insert the n% sign. Basically, it considered all these words as like, we need all these words to be appear for a search. In case of phrase to TS query, basically all those words must be next to each other. So this is the operator for proximity search. And this is how the ranking is done. So this is the actual data, and this is how the query is performed, and this is the score that is returned. The next one is based on the label, and I will cover this one more construct. This is to highlight the matching term. It's not cross-site scripting safe, but Postgres has support for it. So if you see here, the search term is getting highlighted here, like where it actually appears in the document. We are only looking at the building block. I will cover the actual query against the table in another demo. But so far, any questions? Yeah.
The, so for a B tree, there's got to be a ratio of the size of the index to the size of the data index, and the same for full text. How do those ratios compare?
Okay. So I think, okay, so the question is, what could be the index size in terms of B tree and what could be the index possible size for full text search? So in case of, so basically like it boils down to what goes into the index for a full text search. So in case of full text search, individual lexeme goes into the full text search. And since like multiple documents can share those documents, like I can't answer accurately, but like, hypothetically, I can tell that it may not be as large as actual B-tree index because only the unique lexeme goes into the index and those unique lexeme might appear in multiple documents. So the word need not to be repeated multiple times.
I would have guessed, I would have thought the full text would be bigger. So that's surprising to me. So
Yeah. Yeah, the reason I'm thinking it's lesser in the size because in case of, okay, one clarification is full text search index will have index based on the individual lexeme. That means one document can contribute large portion of the index if that helps. So in case of full search text, the index will not represent a single document. Document is broken down into multiple lexemes and lexeme goes into the index. So if you have exactly say hypothetically like two documents exactly same, then the index size will be same as the size of the first document because only those lexeme needs to be stored only once into the index, if that helps. While in case of B tree, we'll have both document going into the index. Yeah.
All right, quick question about the boundary words. If you wanted to explicitly search for a document with boundary words, for example, if I want to find a document with the word the 5 times over, I see a limitation where you couldn't do that if they never get converted to lexemes for the search. Is there a way to explicitly pass those in and search for them?
Okay. So this is an interesting question, right? That we still want to perform the search in a document anywhere. And we don't want the transformation that is offered by full text search. So there is a way, there is one more search that we'll look at later, fuzzy search. So basically, like, how does it work is the operators for the fuzzy search has those unit going into the index. So how Postgres work is it will locate those individual word as an approximate search. Once the result is narrowed down, then it will look for the exact word. So using combination of two different text search type, we can achieve that result. Any more questions? Anyone online has any question? All right, so let me move to the next text search. This is the next topic, like, the fuzzy search or the similarity search. So this is offered as an extension, and once it is enabled, it allows detecting misspelled word. This is the Trigram extension. So what exactly is Trigram? Trigram is a group of 3 consecutive words taken from the text. So how does it look like? So let's take an example of the trigram for the word cat. Postgres put the 2 space as a prefix and 1 space as a suffix in order before it does the calculation for trigram. So this is how the trigram looks for a cat. Now, how the similarity search works. So this is an example where a person's names, like with slight variation, is compared. So for both of them, 2 trigrams are created and similarity is performed based on how many trigrams are getting matched. And that is how the similarity search works using the Trigram plugin. For fuzzy search to work, Postgres or the Trigram plugin offers multiple functions. The first one, sort trigram, displays the trigram for a given text. The next 3 are for similarity search for different use cases. The first version is for finding a typo or a misspelling when comparing almost equally length string. The second one is for performing a substring. So basically a shorter string to be matched against the longer string. Again, this is not actually a substring. Basically, this is at trigram level. So basically trigram from the shorter text is continuously appearing in the longer text or not. Based on that, the word similarity is performed. Strict word similarity is for the whole word. So the word similarity doesn't honor the boundaries of the word, while strict word honors the boundary where we want to match the whole word from a short text to longer text. Now, Postgres also has support for the operators. So like why we need both, like functions and operators. Operators are optimized for index. Index only knows operators. Based on operators, the planner or the optimizer will decide whether index to be used or not. And that's the reason we need these operators. Operators result is a Boolean versus the function returns the similarity score. So functions can be used in a select portion, while these operators will be appearing in a where clause, and the last one can be used for sorting. So again, don't get scared by the actual syntax. Basically, like basic text search used all the good symbols, so we are left with this one. But the first one is similarity, where the misspelling can be detected. The second one is for substring. The third one is for matching the whole word. The last one is a distance operator, which is to rank the relevance, basically relevant result. The relevant result will appear on top based on how many trigrams are getting matched. There are other variations, for example, like commutator of these operators where like left to right comparison versus right to left. The next plugin is unassent plugin. Basically, this is for removing accents or the diacritic from the user input. So this is again another plugin. Once it is enabled, it allows removing the accent. This is useful if the data contains this accent. Now let's take a look at this fuzzy search demo. So this is the syntax using which plugin can be enabled. This is for displaying trigram. And let's look at the result of similarity search. In first one, this is to detect the misspelling, and the second one is to detect the substring. And if you look at the result, the similarity score is low, even though the word appear exactly, because for a similarity search, the length also matters. Since the second substring is lengthier, the overall scores goes down. So basically, like these variations are for different use cases. Like that's what I'm trying to point out. So if you want to look for a misspelling, basically we are looking at like almost similar size string. Like we can still use it. It's just that the score will be less. And this is just to demo that like these are totally different word and it can't be matched. And this is the example from slide where like the similarity score of 0.4 is here. Same way we have word similarity and strict word similarity. So this is for substring, and then the next one is for whole word match. And that's the reason like we'll get different score for the same type of search. So let me put some data inside the actual table. So in this case, there is a typo, and we are trying to find out whether it can perform the similarity match, and along with like the result is getting displayed. So even though the search term has a typo in it, it is still able to match the actual content. The next one is, okay, like why there is no match? Because there is a threshold using which the similarity search is performed. So in case of misspelling, it's just 0.3, while in case of word similarity, it is 0.6. So it expects very high score in order to consider that a match. So this is another search where the similarity is found. This is basically like substring match. And I will just skip because of time constraint to the unassigned plugin. So here the diacritic is removed, and this is where it converted to actual tags so that the search is made possible. Any question on similarity search?
But how did you declare, go to the post table where you created, how do you declare that this is an n-gram or trigram?
No, so here I'm not creating any index. The operator itself is on the fly converting them to trigram and then doing the comparison. Yeah. So unlike a full text search where the result is pre-processed and stored into a separate column, we don't need to do it because trigram is very straightforward versus the full text search, which is much more involved.
That was a scan. Match between.
Oh, so there is an index that I'm going to discuss in the next section. Yeah, yeah. Any other question? So actually, that's actually the next topic for the discussion. So we haven't talked about the indexes for the full text search as well as fuzzy search. So these are the two indexes. The first one is generalized inverted index, and the second one is generalized search tree, which is used for both full text search as well as fuzzy search. There is a slightly different syntax, but there is an index for both type of search. The gene is a go-to index for basically like both type of search. The GIST can used in case where like, the update needs to be faster. So let's look more into that. So generalized inverted index can be thought of as a index at the end of the page where like there is a keyword is mentioned and then number of pages where that keyword is appearing. So that's how it works in case of full text search, where the actual document is not going into the index, only those lexeme from the tx vector lands into the inverted index. It is generalized because it needs to be implemented separately based on the data type, basically. So for text search, full text search, basically out of box implementation is provided. In case of fuzzy search, once we enable the Trigram plugin, it comes up with the operator so that it can works with Trigram. But basically it's given the name generalized because it can be implemented for a given domain to solve specific problem using the data type. Now, if you have made it to this slide, basically this is a trait in case of Postgres documentation. There are not many diagrams. This is the only diagram that I found for gene. And under hood, it uses the B-tree structure. You can see it here. We have a meta page and then root node, internal nodes, and the posting list and posting trees are actually pointers to the table row. When there are less number of rows that are getting matched, it is stored as posting list. If there are very high number of rows are matched, it is stored as a separate structure. Now, in case of gene, you can imagine that since individual lexeme go to index, basically a single document can contribute large portion of the index. And that's why the update operation could be slow. And as a workaround, the pending list is introduced. So whenever the new insert or update is performed, it goes to the pending list. So while performing search, Postgres both goes to the actual tree as well as it also uses the pending list. Pending list, whenever the vacuum runs, basically it goes to pending list and then those document made it to the actual tree. Yeah, anyone has any question? Okay. All right, so now this is like generalized search. This is another index. This is just a framework where it can be implemented again to solve domain specific problem. For full text search, Postgres has native support, while for a trigram, it comes up with the implementation. So how does this GIST is different from the, different from the gene index? So in this case, the document is represented as fixed bit string. For example, like this is just hypothetical example, but consider hash algorithm is applied to the actual, in case of full text, assume Apple is a lexeme. So hash operation is applied and then fixed length bit string is created. Similarly, all the words that appears into the document will go through this hashing algorithm, will result in a bitmap index, and then the OR operation is performed, and that's how the signature for the document is calculated. Likewise, for each child nodes, this bitmap signature is calculated. For parent, it is just about like performing bitwise OR operator for all of its child. So it is like a bounding box. And for each data type, it can be implemented differently. This is how it is implemented for the text data type. Now, comparison between gene versus GIST. Gene is generally faster compared to GIST, but gene is larger in size compared to GIST. As you can see, in case of GIST, only the portion of the document goes to the index. GIST is lossy because hashing algorithm, so can two different words, hash of it might be same, there could be a collision, and that's why it is considered lossy. Lossy in the sense that will not lose the search term, it is just that additional check will be needed while using GIST index. And in some cases, GIST index can return the top end result very quickly. So should I do demo? I think we are almost at the time.
We can skip it.
Yeah, so I will skip the demo. And I will try to maybe take a screenshot and send to the people. Okay. Yeah, so basically takeaway is So considering like, that Postgres has full text search, fuzzy search, and like including normal search, is it a replacement for Elasticsearch? No, it is not. Elasticsearch is a massive distributed system made for a scaling, but there will be use cases which can be satisfied by powerful text search capabilities offered by Postgres. And the advantage is, in case the given use case is satisfied by the Postgres, there is only simplified stack. It's already getting used, and we don't need to introduce any new technology. It's cost effective. Basically, you don't need to provision additional resources. And basically, like if I want to give one real life example. Like I came across an article which is like very old, but it has a mention about GitLab using full text search for its operation. Of course, I'm not sure whether it is used today or not, but like this is really powerful capability that is worth exploring, and that might be sufficient for many use cases. All right, I stop there and I will wait if anyone has any question.
Snehal,
Yeah.
I just want to say thank you because this is a great, for being a SQL Server guy like I am, it's a great comparison that I see between the two. And it seems like Postgres is full text search is much more integrated into the database engine, where SQL Servers is a separate service. And then also Postgres seems more robust. It has many more indexing methods and search methods as well. So thank you.
Yeah, and thanks for like, your comment. Like this is like another way to look into the world that like I'm not familiar with. So yeah, it is good to know about like what's going on in different technologies. But yeah, like anyone else has any questions, comments? All right, so I think like we are almost over, and I will add additional details.
Thanks, Neha. Very good. Yeah, something calling. Or to the desk.